Hi, this is a video that I make to fix a mistake in the slides about the running time of the worst case uh, partitioning when the worst case partitioning happens in quicksort. And when we analyze uh, the recurrence of that worst case, we basically obtain some arithmetic series like equations. So there's a mistake in the original slide, and I'm gonna fix that here. So know that the most unbalanced partitioning happens when the resulting two subarrays has n-1 elements and 0 elements. So that's why we have the recurrence in this form, like T of n equals T of n minus 1 plus dn. Okay, so I use a specific function d of n to replace big theta of n, so that our next step of proof can be actually done, right? With the big theta, we can never do some actual mathematical transformation, right? And we just need to know that d is some constant that defines the partition cost. Okay, so this is the recurrence that we are working on. All right, so our guess is that this the final solution could be could be a quadratic function, because if we further split t of n minus 1 into t of n minus 2 plus d times n minus 1, right? And further split t of n minus 2, then eventually we're gonna obtain something like this, right? This is a very typical arithmetic series timed by some constant d, okay? And the summation of a arithmetic series can be expressed by some quadratic function, okay? Because the summation of it can be expressed by a quadratic function. So our guess is that the T of n should be bounded by, should have a upper bound. And actually in this case, the tight bound as geometric of a quadratic function, okay? So basically we will prove the upper bound first, okay? We use the substitution method, and we assume that the quadratic upper bound applies to a smaller case, which is t of n minus 1. So we assume that this is correct. And we substitute it into the original recurrence, okay? And the original recurrence is like this. So we substitute this one with the upper bound on the right. So we will obtain something like this, okay? And we also want the solution T of n also has the quadratic upper bound, which means we want that we want that this thing on the right should also be bounded by c times n squared. Okay, so now we have a inequality that can be solved, and the inequality is like this. Okay, c times n minus 1 square plus d times n is less than or equal to c times n squared. Okay, so if we expand the term on the left, it is c times n squared minus 2n plus 1, right? And then we can eliminate the term, the quadratic term c times n squared, and then we will have this inequality. The c should be greater than or equal to n over 2 times n minus 1 times d. Okay, so this inequality means that as long as c is greater than or equal to this value, then this inequality will hold. And that is exactly the result we want. Okay, so now, but c is not fully solved yet because there's an n in it. Okay, but observing this term, the coefficients n over 2 times n minus 1, we know that this term has an upper bound. Okay, this one cannot be infinitely big. So especially when we look at the values, though, if we look at this function, we know that when n increases, this value, the n over 2 times n minus 1, will approach some limits. And when n equals 1, the upper bound of the function is reached, which is 1 over 2 minus 1, which is 1. Okay, so the maximum value, the maximum value of this coefficient is 1. Okay, so as long as C is greater than 1 times D, then this inequality is always true. Okay, so that's the C we want to find. Okay, so we can choose C that is greater than D, and also we also notice that this is the inequality will always hold true as long as for n that is greater than or equal to 1 actually. Okay, so the solution, basically the solution is correct. Okay. Next, let's go through the general principle of substitution method using some examples. Okay, so the idea of substitution method is basically mathematical induction. And the purpose of the mathematical induction is to prove the asymptotic notations that we want to prove is true. Okay, so for example, let's use the upper bound as an example, and we just use the example in the previous video. Say the recurrence is like this. Okay, and the thing the asymptotic property we want to prove is that T of n could be having a quadratic upper bound. Okay, so the meaning of this big O notation is that we can, if we draw the functions like this, the meaning of this is that we can find that the function T of n, suppose that this is the curve of T of n, should be bounded by a quadratic function, say c times n squared, when n is sufficiently big. Okay, when n is to the right of n0, if we can always show that T of n is bounded by this c times n squared, then we are basically done with the proof of this big O notation. Okay, so but we know that there are infinite possibilities to the right of n0. There are whole infinite amounts possible values for n that we can choose from, right? So the practical way is that, okay, how do we show that T of n should be, how do we show that T of n should be lower than c times n squared for all n that is greater than n0? Okay, so we basically need to use mathematical induction to prove this. Okay, and mathematical induction is based on the idea that if you can find that for n1, say n1, you can show that for n1 this upper bound holds, and to a larger value n2, this upper bound also holds, then you basically show that if n1 is true, then n2 is also true, and n1 could be an arbitrary value, arbitrary choice. So you basically show that for any values to the right of n0, this upper bound is true. And of course, n0 should also hold. Okay, so that's why the n0, the boundary case for the mathematical induction, is also important. Okay, so the way we choose n1 and n2 is to use the original form of this equation, okay, of the recurrence equation. So if t, for the smaller case, t of n minus 1 is bounded by c of n minus 1 square, and the t, the original, the larger case problem is also bounded by the quadratic bound. So if we can infer from this above equation inequality to the below inequality, then the mathematical induction is done, right? Because this is the smallest case. This is the n1 now, and this is the n2 now, okay? So we can basically substitute, okay? Substitute t of n minus 1 with its upper bound. Right? And we want to infer, to step from this inequality to this inequality. Right? As long as this inequality. So if we choose the values of C properly, this inequality, this quantity will be automatically smaller than this quantity. Then our proof is done. So the trick part is to how to find the C that always make this inequality valid. Okay, so we want to solve these inequalities a little bit. So eventually we will get to C should be greater than n over 2n minus 1 times d. Okay. And d is the constant. Okay, so as long as C satisfies this quantity, then we can automatically infer from this smaller case to the larger case. Okay, and that means it's basically true, the upper bound is basically true to everything to the left of n0. And of course, we need to find the n0, right? So here, we just need to consider the upper bound of this function, because this function is pretty special. When n equals 1, it has its upper bound, which is 1. Okay, so we just need to use the C that is greater than D. Then this whole inequality is always true for all the n's possible. Okay, and that is one example of the general principle of mathematical of substitution method. Now I will use a more strict, I will show a more strict proof on why the T of n is has a tight bound expressed by the big theta of n squared. Okay, so this big theta n squared means that we want to find the constant C1 and C2 and n0 so that the T of n is greater than C1 times n squared and less than C2 times n squared for any n that is sufficiently large. Okay, because in the previous step we have basically proved this right part, the upper bound. So now we just need to use the substitution method to prove the left side, the lower bound. Okay, So everything would be quite similar unless the direction of the inequality is inverted. Say we want to, so we assume that for the smallest case, the lower bound applies. I use C1, okay? And we want to infer from the lower case, from the smaller case to a larger case, which is Tn, which should also satisfy C1 times n squared, okay? So we substitute this inequality to the recurrence. T of n should be T of n minus 1 plus D of n should be greater than C1 n minus 1 squared plus Dn. And we want this thing on the right to be also has a lower bound of C1 times n squared. Okay. And then this is the same inequality that's with only the flip around of this inequality direction. So we basically can infer that the C1 should be greater than or equal to, or should be smaller than or less than or equal to n over 2 times n minus 1 times d. Okay, and we know that this quantity, this function has a lower bound. Okay, the lower bound is when n reaches approaches limits infinity. So this one will always be smaller than. Will also always, this quantity will always be greater than 1 over 2. Okay, so as long as we choose C1 to be 1 over 2, okay, then this inequality always hold. Okay, so the C1 should, we can choose the C1 to be 1 over 2 times D. Okay, or even smaller values. Okay, so combining with the previous conclusion, if we let C1 to be smaller than 1 over 2 times D and C2 to be greater than D, then we can always have C1 times n squared is bounded, T of n is bounded by this lower bound and the upper bound. And that's the proof for the big theta notation.